All right, thanks for coming, everyone. Today we have John Christian with us. He is a postdoc working jointly at UTIG with Ginny Catania and Georgia Tech with Alexander Roble. He's working on ice dynamics and how they interact with the climate. So we're going to hear some about the work he's been doing for the past year.
All right, thanks, Erin. All right, yeah. So this is the work I've been doing in the past year with Ginny and Alex, and so to kind of set the scene here, what I'm going to be talking about today is variability of these marine terminating glaciers that drain the great ice sheets. So this is southern Greenland from space, and there are also these large outlet glaciers in Antarctica as well. And what we've been looking at is the variability and large changes of these glaciers, and specifically what their sensitivity to their local bed topography means for how we interpret the changes we've seen, and whether they're due to natural variability or anthropogenic forcing. So that's the kind of overall motivation here. And so so these outlet glaciers have undergone rapid retreats, especially in the last few decades. So on the left is a compilation of retreats all around Greenland. So since the early 2000s, there have been these large multi-kilometer retreats in pretty much every sector of Greenland. And things look a little different in Antarctica. The kind of scale of the systems is a bit different, but also in many sectors of Antarctica, especially West Antarctica, we've seen retreat of the grounding line. So this is Pine Island Glacier, one of the major outlets that's changed dramatically in the last few decades. And while most of our observations of these changes are concentrated over the satellite era in the last few decades, where we do have longer records, there's evidence of early phases of retreat too, earlier in the 20th century. So the left is the kind of aggregated retreat rates in southern Greenland, and these were compiled from satellite, and then for the earlier years from aerial imagery, so going back to about the 30s, when there was a phase of rapid retreats in Greenland. And then other lines of evidence on the right shows calving rates for this one large outlet glacier that were inferred by sediment cores in the fjord in front of the glacier. So, and that also showed this phase of retreat in the 30s and 40s. So what do we know about the forcings that are driving these retreats? So the attribution is actually somewhat equivocal, although surface warming over the high latitudes on average has been formally attributed to anthropogenic warming. Things are a lot noisier at local scales, and we also have this really robust ocean variability to contend with for marine terminating glaciers. And this composite figure kind of illustrates that nicely. So these blue bars indicate periods of time where this large outlet glacier in Northwest Greenland was undergoing rapid retreat throughout the kind of starting in the late 19th century. And the blue time series are ocean temperatures from a mooring in Southwest Greenland. And the red time series is surface air temperatures closer to the glacier front. And so you can see there's maybe a slight warming trend, but a lot of variability, both interannual variability and then these kind of decadal, multi-decadal changes. And then so the bottom time series is the AMO index, the Atlantic multi-decadal oscillation, and this is a very prominent kind of mode of large scale climate variability, which kind of lines up with these phases of retreat. So there's a strong connection here to at least the timing of these retreats and these modes of natural variability. And this kind of applies to Antarctica too, where we know that decadal ocean variability is a big driver of the changes we've seen recently. So we've made progress as a field kind of understanding the specific forcing mechanisms as far as ocean forcing and so on. And we're starting to get at the anthropogenic fingerprint in those, but there's still a large role of natural variability in pacing these forcings. And so broadly speaking, the anthropogenic component of the recent changes we've seen is still kind of uncertain in a quantitative sense. So the noise is one challenge, but another issue is that these glaciers, most of the large retreats that we've seen are associated with retreats from submarine topographic peaks. And so this is a figure from some of Ginny's recent work. This is a glacier in West Greenland, and it was observed to retreat off of its terminus retreated off of a bed peak in the early 2000s and retreated back through deeper water. So the black line here on the right panel is the submarine topography, and it retreated rapidly through and over deepening back to another peak. And we sort of have a theoretical basis for understanding why these retreats occur rapidly once they retreat off of submarine peaks or sills. So there's a dynamical instability that kicks in if the glacier is sufficiently perturbed, and then once it's in deeper water, it can retreat very quickly. So we have these kind of threshold dynamics at play when we have glaciers retreating off of these topographic peaks. And so in the context of natural climate variability, and then also these kind of threshold dynamics, that poses a question of when we see a retreat like this, was it triggered by natural variability or anthropogenic forcing, and how do we kind of make sense of that question? So our goal has been to start thinking about what a formal attribution framework should look like specifically for these sorts of glaciers. And so first, we've just kind of been laying the conceptual groundwork. So what I'm going to show is mostly modeling results to kind of get at the general dynamics that are controlling things here. And before I go into our results, I kind of just want to back up and talk a little bit about just what attribution studies really are. And so to start with kind of just the most fundamental attribution question in climate science is that of just global mean temperature. And so we now have very confident attribution that this can be attributed to anthropogenic forcing. But the way we can make these assessments is based on running models with and without anthropogenic forcing. So attribution is all about kind of comparing simulations of the world we think we're in and a counterfactual world without human forcings. And so, yeah, the orange simulations are including all known forcings and showing the temperature anomalies, including all known forcings. And then the bottom is with only natural forcings. And of course, only the simulations with all known forcings, including anthropogenic, match our observed warming. So that's, this is a line of evidence for very confident attribution of this warming to human causes, right? So, so this is kind of shows kind of conceptually what we mean by attribution. And it's always important to think about what are the relevant dynamics that we have to capture in these simulations in order to make a confident statement. So here it's based on these, these kind of comprehensive global climate models. But then there are also kind of secondary attribution questions more specific to certain subsystems of the Earth system or certain events. So, and then these each have their own considerations. So another one that's become very common in the last decade, especially, has been attribution of individual extreme events. And this used to be thought of as something that we couldn't really do because these are fundamentally kind of stochastic events. But now there is a formalized framework for understanding the anthropogenic role in extreme events like heat waves and so on. And this is framed probabilistically now. So On the left, we see these distributions of some generic climate variable, and now attribution for this for these cases is framed as how does anthropogenic forcing shift the distribution and make a given event more likely. And so one example of this was the European heat wave of 2003. This was kind of the first formal event attribution that was done. And they were able to look at climate model simulations, look at the extreme events in these climate model simulations, both with and without human forcings, and conclude that events of this magnitude became more than twice as likely due to anthropogenic changes. So that's this is kind of another version of attribution. And then again, it depends on capturing your models capturing the dynamics of these extreme events. And then getting a little closer to where we're going, another example is mountain glacier retreat. So this is a very iconic change in terms of anthropogenic changes. These large retreats since the beginning of the industrial era. So this is a map showing the retreat of a glacier in the Alps. So in this case, we have to then incorporate the ice dynamics that determine how glaciers integrate both natural variability and long-term trends. And so this was incorporated recently into kind of a formalized framework. And what I'm showing here is this figure from this study led by Gerard Rowe and others. And what they did was look at how natural variability is integrated by these glaciers. So glaciers respond to year-to-year variability by producing their own kind of more low frequency terminus fluctuations. And that is what you have to compare an observed change against in order to say whether it's beyond the sort of natural envelope of variability. And it turns out for mountain glaciers, they end up filtering out some of the noise, and the terminus retreats we've seen are a very clear indication of anthropogenic warming. So, but getting towards marine terminating glaciers, these systems are a bit more complex in that they're interacting with the ocean. And then, as I mentioned earlier, they have this strong sensitivity to their bed topography, which can modulate their retreats. So this is what we've been thinking about. What are the dynamics that we need to incorporate in an attribution framework for these glaciers? And these are, again, very complex systems. We're kind of taking a first step here and just focusing on this phenomenon of rapid retreats from subglacial bed peaks as kind of a first step for developing an attribution framework. So now the kind of first step in this is defining kind of what our null hypothesis is, and that's, can natural climate noise alone trigger retreat from these bed peaks? And so we're investigating this just with a simplified modeling framework. This is our idealized glacier here, just a 1D simplified glacier, where we have accumulation in the ice sheet's interior, and that's conveyed by ice flow to the marine margin, where ice goes afloat and is discharged by calving of icebergs or directly by melt. And in this particular case, we've set up this geometry so that the glacier's terminus is grounded within about 1 kilometer of a very distinct bed peak. And so based on theory, we expect that it's stable on the prograde, the forward side of this bed peak, but if it's perturbed into the retrograde slopes, so where it reverses and gets deeper inland, that would be an unstable regime. So if we force this glacier with natural variability, here we're using just a synthetic time series of random decadal ocean forcing. So that's shown here in blue. And this is a far cry from the complexity of the real systems once again, but this is just sort of a generic ocean forcing mechanism. You could think of it as anomalies in the direct melt at the ice-ocean interface or in calving. The main point is that this is an anomalous flux at the marine margin. And what this does is it forces the glacier to fluctuate around. So again, this glacier is integrating this variability, producing lower frequency fluctuations. So this is the terminus position here. And it's fluctuating on the prograde or the stable side of the bed peak. And it's pretty much staying away from the retrograde slopes for the first couple thousand years of the simulation. But then abruptly at around year 3000, it retreats back from the peak and we see this rapid and irreversible retreat. So this is the kind of response that we're after here, where variability alone has triggered this large, rapid and irreversible retreat. And again, to emphasize, there's no kind of imposed climate trend here. This is just an unlucky draw of the random forcing that caused this. Yes, it appears that noise alone could trigger retreats from these bed peaks. But we want to know how often to kind of keep formulating this null hypothesis. This also prompts us to think about whether these retreats are really a trend that is going to gradually emerge from the noise, or whether they're more of a stochastic event. And so this has motivated us to think about this probabilistically. So our approach is to run large ensembles of simulations, each with a different realization of climate variability and nothing else different between each simulation. And so we can look at these ensembles and see how often they produce a retreat. So I'm starting here with a kind of a boring case. This is the same glacier I showed earlier in 1,000 different simulations. And over 150-year interval, we see that none of the simulations produce an unstable retreat. But if we crank up the variability a little bit, stronger random ocean forcing, we can get, in this case, 15% of simulations to produce kind of a spontaneous retreat off of the bed peak. And we're just kind of defining this arbitrary threshold of 4 kilometers of retreat during the simulation, just as a way to sort of count up these retreats, but they also keep retreating past that. So we did this here by kind of cranking up the ocean variability. There's a lot of other parameters that can be tweaked to kind of change these probabilities of retreats. And I won't go through all of that, but the main point is that however parameters might vary between glaciers, the main things to consider in terms of probability of driving one of these retreats is just the baseline proximity to the threshold. So how close our terminus on average is to the bed peak, and then the magnitude of its stochastic variability. And in retrospect, these are kind of 2 intuitive factors. If we think about the glacier having this natural envelope of variability, kind of with this schematic here of a distribution of terminus positions. And we're thinking about how often these natural fluctuations approach this topographic threshold. And so, of course, we want to think about how close that is to the threshold and then just the width of this distribution. But it's not quite as simple as just saying, does it ever touch this threshold? Because as you'll notice, even in the case where we didn't see any retreats, so on the upper left, there are times where the terminus briefly fluctuates past the bed peak, but then it recovers before undergoing one of these unstable retreats. So this is kind of an interesting effect. And the nice thing about these ensemble methods is that we're essentially generating these large synthetic data sets that we can then kind of probe to look at the glacier responses. So we can look at take all of these cases where the glacier has retreated and ask what is special about these simulations. Generally in these simulations, the timing of the retreats is random. But if we collect all of the simulations that retreat and then just kind of synchronize their timing so that we just line them all up so that the time that the terminus crosses the bed peak is time 0, then we can do some analyses. So if we do the same lining up of the natural variability that force these glaciers, we can see what the melt anomalies look like that end up triggering these retreats. And so that's shown below here. And unsurprisingly, we see, these retreats coincide with large anomalies in the frontal melt, and the red line is just the ensemble mean. So this isn't too surprising, but what we can do is then compare to cases where the glacier retreats a little bit past the peak, but then recovers. And if we do the same kind of synchronization, we can see that these retreats also are associated with anomalous melt. But if we kind of compare the average anomalies between these two cases, we see that it's not necessarily that the melt anomalies have to be larger to drive sustained retreat. It's that they have to be more persistent. So looking at the red versus blue curve here. So these retreat thresholds are kind of time dependent. They depend on how long the anomalies persist and sort of how long the glacier has been integrating those anomalies. And so this is going to be an important thing to keep in mind as we move towards kind of our eventual goal of thinking about how anthropogenic forcing changes things. So this is kind of what we're here for, right? The attribution question. So I'm going to take you through just a synthetic attribution experiment. So we'll start with just a very simplified scenario where in the background of all this natural variability, we just add a simple linear trend. And we can set up an ensemble for each of these cases, on 1,000 realizations for each, and then compare the ensemble results. And so note here that the trend that I've imposed in the background is pretty small compared to the noise. And so this is kind of the ballpark we're in the real world, as I showed at the beginning, where background trends are generally weak and not super statistically significant. But the ensembles give us a way to kind of look at what the average impact of such a trend is. So in our null case, so this is the gray curves, our background probability of retreat as estimated by our ensemble is just a little over 10% over 150 years. But with the gradual climate trend added, that's multiplied by more than 5. So here we can say that even though retreat is still this probabilistic phenomenon, the addition of a background trend dramatically increases the chances that a retreat will happen over a given interval. So this is the basis for being able to make a probabilistic attribution statement if we could set up these experiments for real glaciers. And just to add a little bit of nuance here, the linear trend is obviously a huge simplification of the forcing scenarios. There's a fair amount of uncertainty in what the actual shape of this forcing should be at especially at regional scales. So we'll just kind of consider another idealized but alternative case here where the same total forcing in the frontal ablation is applied, but only over the last 50 years. So when we do that, we again see an increase in the probability of retreat compared to the null case, but it's not nearly as dramatic as when the trend is applied over the entire interval. And so this just again highlights the kind of time-dependent nature of these thresholds. And in this case, it indicates that the early stages of anthropogenic forcing might be really important to constrain. If we don't know what our forcing scenario is like, especially in these early years, that might leave a fairly big uncertainty in our attribution statements. And this is this difference is ultimately due to the glacier's response time. They're integrating their climate forcing over a period of decades, and in the kind of late forcing case, so the turquoise, the glacier just hasn't had quite as much time to start integrating the background trend and getting closer to that retreat threshold. Again, we can kind of think about the distributions shifting closer to a threshold, but unlike something like heat waves or a different kind of event-based attribution question, like I discussed earlier, for glaciers, the distributions don't shift instantaneously with the climate, but they lag it depending on the glacier's kind of response times. So there's an important distinction to be made for these glaciers. And then the last little bit here is to look towards a population of glaciers. So we've been focused on this single idealized case, but around Greenland, for example, there are close to 200 of these outlet glaciers, and they all have kind of unique geometries, and the responses that we've observed have also been heterogeneous. Although there's widespread retreat, the amount and the timing has varied a fair amount around Greenland. So just to kind of start thinking about how attribution might look for a population of different glaciers, we've also investigated a bunch of synthetic random geometries. So these are just two examples where we've put glaciers on these kind of random bed topographies. And when we do this, we find that their equilibrium positions are, there's a distribution in terms of how close the terminus is to the closest bed peak. So that distribution is shown here on the bottom. And basically the takeaway here is that with this topographic kind of heterogeneity, we should expect a spread in the sensitivities of individual glaciers. So there's going to be a range in how close they are to their retreat thresholds. And so then in that case, if we're doing a more of a regional assessment, we might then look more at how many more glaciers would retreat due to an anthropogenic trend, rather than the changing probabilities of individual glaciers. So this just shows, again, kind of a synthetic attribution experiment for the whole population of glaciers. So on top is the climate forcing scenarios. Both have variability, and then only one has this externally forced trend. And then on the bottom is the terminus position for the whole population of 200 glaciers. So each gray line is a different glacier with a different bed geometry. And so on the left, without a trend, they kind of fluctuate coherently in response to the climate variability. And there's kind of just this one glacier that happened to be triggered into a larger retreat by the natural variability. So the black line is this retreat threshold that we've set. But if we add a background trend, we see that there's suddenly a ton of glaciers that are going through large retreats. And then note that some of the retreats are relatively small, some are 10 kilometers. So there's still going to be a fair amount of heterogeneity in the response we should expect. But I think the takeaway for attribution is that we can frame it as how many more retreats have we actually observed than we would have expected with no anthropogenic forcing. Yeah, so to just kind of wrap up, the takeaways here are that the combination of internal climate variability and the kind of threshold dynamics characteristic of these marine terminating glaciers make for an interesting and challenging attribution problem. But we think that we can approach this in a probabilistic way, using large ensembles of simulations and thinking about what is the probability of retreat from these topographic peaks over the industrial era. The sort of big takeaway is that persistent trends, even if they're kind of weak compared to the noise, can dramatically increase the probability of retreat. And then the entire forcing history is important for attribution, because this is a very, very time-dependent problem. And so, yeah, so this is just kind of, we're laying the groundwork for future attribution experiments. And there's going to be a lot of kind of individual characteristics to consider for individual glaciers. But I think this, especially this effect of persistent trends is really robust enough to really motivate looking into this for specific glaciers and moving towards more formalized statements about the anthropogenic role in the retreats that we've observed. So yeah, I will wrap it up there and take any questions. Thanks for listening.
Awesome. Thanks, John. If you have any questions, just go ahead and unmute yourself and ask. I can start off. So like in this middle plot where you're showing kind of a huge suite of models, are these like, are they physical, like 2D sort of box models that you're doing? Is it just like a sort of 1D integration over a line to kind of see like what happens with retreat and advance?
Yeah, so it's a 1D. I'll just go back to the like little cartoon of the idealized glacier. So it's just a 1D model. So it's just looking at ice flow along a flow line, and it's basically just solving the shallow shelf equations. It's a approximation for ice flow dominated by sliding. So it's a very simplified modeling framework, which is in part necessary for these kind of large ensembles of simulations. So that was, it's been a good approach for kind of all of this exploratory work. But I think because it's such a simplified kind of 1D framework, the real glaciers are very much, 3D creatures. So we'll have to kind of think about the kind of computational trade-offs between being able to run a bunch of simulations, but also including the complexity that we need. So.
Mm-hmm. Cool.
Yeah.
Hey, John, cool talk. I have a question. So you mentioned that this model could be expanded to incorporate maybe regional trends. How do you envision that happening? Like, how do you envision expanding this probabilistic approach?
So do you mean for like the regional collection of glaciers, or just for a particular?
I guess for like a regional collection of glaciers.
I think, yeah. So I think it's going to be, so I guess our kind of next plans are to start with individual case studies. And then I think it'll be a matter of kind of assessing like how many glaciers in a region we could actually simulate with enough constraints. Cause that's a good point, that like at a regional level, like we're going to have fewer and fewer glaciers that have good constraints. So I think at a regional scale, the kind of resolution, I guess, broadly speaking, for any glacier is going to be much lower, and the sense of attribution for any given glacier will be shakier. But so there are some modeling frameworks that now are kind of simulating the whole ice sheet and able to resolve individual outlet glaciers, which are they're still a lot coarser than like the detailed simulations that people are doing on particular glaciers. But I think as long as you could build in some of a fair amount of the topographic variations that we think are probably controlling these retreats, you could start running simulations at a regional scale. But yeah, I haven't thought quite that far ahead. I think kind of next step is like building in realism for like a given glacier. But yeah, that would be the ultimate end goal, is to kind of look at the regional scale.
Very cool. Yeah, I'm interested to see how this work develops.
Thanks.
Thanks.
Any other questions? All right. Well, thanks, John, for showing us this. It's nice to get a little diversity in our program.
Yeah, thanks for having me, and thanks for tuning in, everyone.